What will happen? If I use Euclidean distance, will I be still admissible?
Yes.
Will I be as informed?
No.
No. That's the reason why we use Manhattan. You see what I'm saying? Euclidean is even cheaper. By the way, Manhattan distance is not that hard. It doesn't look like, it doesn't, if you ever seem to be writing a 15,000 line code to compute the Manhattan distance between two coordinates, hit yourself on the head and realize that it is just this. That's it. Okay? The difference between that and the other one is x1 minus x2 square plus y1 minus y2 square. Okay? These are all good, well and good. So we found that Manhattan is better than in Euclidean, so we are happy with that. Now here is my other thing. Can I get better, in the textbook they have talked about those two. But can I get even better heuristics like the one that I did for the path planning problem? By, for example, I went from circular approximations to polygonal approximations. That would be more informed while still being admissible. What can I do for tile puzzles? What I can do for tile puzzles is the following. If I'm trying to compute the distance between this and this, instead of either number of displaced tiles which I did, or the Manhattan distance which I also explained to you. Here's another thing I would say. You notice that I put some tiles in red. Here's an idea. Suppose you're all outside of the class. I want to put you back, remember where you are, that's your actual configuration. And I throw you all outside the class and I want to put you back into your places. And imagine every person needs to be walked to their place and so on, that's the cost. I would argue that the total cost that I have to spend in walking every one of you to your correct places, which is what tile puzzle will be doing, will be at least as much as the cost I will spend trying to walk all the women to their places. This is not patriarchal. I'm just telling you that women are a subset of all the class. They're actually a nice small subset. Thanks to being a STEM class, there are only 30 of you. Okay? And if I put all 30 of you in your right places, and I count how much cost I incurred for that, that's definitely a lower bound on the total cost I have to spend getting all the rest of you to your places. You see what I'm saying? So, basically I would say I would define a pattern. In this case, the pattern happened to be women. Or I can say my pattern is, let's put all the people with long hair into their place first. And then we'll put the rest of them. And my heuristic would be just counting the cost of getting these distinguished people into their places. And I'll only compute that cost. In doing so, remember the way I did, I had other people just basically, the rest of you don't matter, when I'm looking at the special ones. So long-haired people are being put in their seats, non-long-haired people are indistinguishable. They are just warm bodies. That's pattern databases. So what I basically do here is, I need to get this to this, right? This is the heuristic cost. I want to estimate that. I will argue that in the final configuration, you notice these guys are in the fringe. These are the red. They are on the fringe. Whatever is the total number of moves I have to make to get all these guys into their right place, that would be lower bounded by solving this problem. Where only things that I care about are the red ones. The other tiles actually have no individuality. And so the difference between this being here is the same as the other way around. Which was quite different when they actually had numbers written on them. Do you see what I'm just saying? Now, this gives you a beautiful way of computing more and more costly heuristics. Now, that looks like a perverse thing. Why do I want to compute costly heuristics? Why I want to compute costly heuristics? Because they will be more informed. That will reduce the time, potentially, the number of node expansion. So really, this is pattern database expansion. And I want to tell you two things and then we get to go. One is this one, you need to understand that you now have to do a different search, which essentially involves trying to compute the optimal distance, optimal number of moves you have to do in terms of length to get this configuration into this configuration. And it turns out that's going to be a really costly search in itself. It's not something like plugging stuff into the formula. In particular, this is basically what happens. What you would do is rather than compute each node's distance from the goal node, before you even start the problem, you compute the heuristic values for all the nodes. And in one pass, the way you do it is you start from here and do breadth first search. Breadth first search. And whenever you get a new configuration, that will be the first time you would have seen that configuration. That's the cost of that configuration. Amazing idea. But it takes time to do this. The bigger the pattern, the more time it's going to take. That gets me to this last thing that I want to show before we leave for today, which is this amazing picture. You should remember this. It should just start out getting printed on your head. There are two kinds of costs which decide the total cost you spend per search. One is the cost of heuristic. The other is the cost of search when you are using that heuristic. The cheapo heuristics of the kind everybody's heuristic value is 0, take 0 cost to compute. But they take humongous amount of cost to actually do the search. The real costly heuristics like H star will take as much time as the original search. But then once you do that, the search itself is extremely cheap. So in a sense, in a way, if you're stacking up the heuristics from the least to most informed, their cost is going to increase like this. And for each of them, the cost of doing search with them is going to reduce like this. Somebody asked, what's the right level of abstraction? This is the picture. Right? Essentially, you have to figure out where they intersect. And that's the best level of abstraction. What was interesting was in the beginning, for the longest time, people used to think that this crossover point is likely to exist on this side. So they would assume that if it is to be a heuristic, it should be something that is a closed form solution. I just plug it in. Now we are much smarter. We realize that in fact for many problems, it requires pretty costly computation just for the heuristic. And yet the total search cost, which is heuristic cost plus the search cost, will reduce. Keep this in mind when you try to do the second part of your project, because if you only look at easy heuristics, you will come up with a heuristic fast, but you won't get best search.
Yeah, I know. I think I want to take that down, so